To this month's New York Haskell meetup. We have two really exciting talks tonight. I'm excited about both of them. Couple quick announcements up front, and we're going to make them again later because they're important announcements. First, next month, Pivotal Labs is moving. They're going to have a new location over on like 6th and 18th. And we'll have that information with the meetup, but it's going to be at a different location than it has been, so make sure you don't show up to the wrong place next month. And also next month, we're actually not having a meetup in September proper. As it turns out, the last week in September when we normally do it is the International Conference on Functional Programming. It's in Boston. A lot of us are going to be up there at the associated workshops, including the Haskell Symposium. We are getting a speaker who's coming into town for the Haskell Symposium to come down to New York afterwards. And the first week in October, I believe October 2nd, Luite is going to be coming and speaking to us about his work getting GHC to compile to JavaScript and the GHC.js compiler that lets you run Haskell in the browser, to some really, really cool stuff as well. So that's going to be the next meetup is actually October, I believe, 2nd, and it'll be at a new location, and it'll be on GHC.js. And then at the end of October, the 5th Wednesday in October, Paul Hudak will be coming to speak, one of the original members of the Haskell committee, I believe, and he'll be talking about functional reactive programming and really whatever he wants to, because it'll just be great to have him. So our first speaker tonight is going to be Anthony Cowley, and he does stuff with Haskell, and primarily he does stuff with robots in whatever language he finds sort of the most useful and necessary in order to get a lot of very real-world things done that involve things that, if they go wrong, can destroy equipment that one doesn't want destroyed and burn through grant money. If you're lucky, that's all that it's going to burn through. Some of these machines can. So he'll do a great job, I'm sure, telling us all about his field, and I'm really excited to have him. So take it away. You want to clip on your
All right, everyone can hear me? Yep. Okay, so Gershom actually just spoiled my story. He described robotics very accurately. So I'm a graduate student at the University of Pennsylvania at the GRASP lab. It's one of the largest robotics labs in the country, possibly the world. I mostly do computer vision, generally perception for robots, also multi-robot coordination, and software design for robotic systems. This includes programming language-based verification and general architecture questions. So this is going to be a really, really high-speed tour through a lot of pieces of the Haskell world so we can see how they apply to robotics. It's not going to be a detailed tutorial on all of these things because I want to give you working examples of every last piece we cover, and so all this code's open source and you can peruse it whenever you choose. I want there to be something for everybody, okay? So it's going to move fast, and that also has the side effect of showing you what robotics is like. Robotics is really broad. Any tool available to me, I want to use it, okay? That's really my attitude towards things, which raises the question of what is a roboticist? Broad terms, an engineer solves problems. A roboticist solves problems using all available technology. An engineer is going to be conservative. They're going to say, stick to what you know, use the tools you trust. If something looks unfamiliar, distrust it because it probably means something is wrong. This is like trusting your gut feeling, and it's a superstition that comes from experience because engineers see things go wrong and they can't let it happen again because engineers are asked to solve problems using tools that aren't fully understand. Yes, we're applying math and science, but new materials come out. New understandings of the world are developed, and this affects engineering. So engineers are operating in uncertainty, so we rely on experience. But a roboticist has to take that conservative core of an engineer and pair it with an enthusiasm for the new that you would associate with a technologist in general. And the glue that binds us all together now is software. Because software gives you a workbench that's infinite. You can fail and fail and fail time and time again and pull pieces from those failed experiments and still build something up. So you're able to pull in the new technologies that you don't know how well they work. They have their weaknesses. They're going to break. They're going to fall apart. And you are, come hell or high water, going to make this thing work just through the sheer application of software. So we're going to take engineering and we're going to bring some new pieces to it. So this is kind of my motto for it, all right? Now, what a roboticist is something I can answer. A slippery question is, what is a robot? That's a lot harder to answer, and maybe everyone's going to be able to provide their own answer as the talk goes on. Some of us have sort of benevolent images of what a robot is. Some of us are a little bit more apprehensive about the future. Interestingly, perhaps not unsurprisingly, kids have a better grasp on what a robot is than their parents. Parents are, we have a frame of reference from Hollywood fantasy of what a robot is, whereas kids compete in things like FIRST robotics. They have siblings who go to college, do RoboCup. So these kids say, a robot is a motor and some batteries and some wires, and you write a lot of software, and then it falls over a lot, and it gets broken. And so anyways, whatever your vision of what a robot is, you say, this is really cool, I want to do this. So you go to graduate school thinking this is going to be nonstop awesome. And the environment is slightly underwhelming because you're going to spend all your time sitting at a keyboard typing away, right? I mean, this is what engineering is today, frankly. If you do theoretical robotics, this is the end of the story. I mean, there's more whiteboards perhaps than this picture, but this is pretty much it. If you do experimental robotics like I do, then it's slightly more interesting. I mean, yeah, you're still at a keyboard all the time, but occasionally something does blow up right in front of you. And that's not hyperbole. I can tell you stories of things blowing up on my desk. So a great development in engineering research over the past few years, I say great, that's an opinion, is the popularity of videos. So a fundamental problem with engineering research in academia is that as an engineer, if you build a system, you spend 90% of your time or more doing systems integration. You spend your time doing things that you can't put into a paper. So the temptation historically has been to not do the systems integration. Maybe just identify parts and claim that if you were to put these parts together, you'd have a really great system. But then don't do it, because you're not going to get credit for it. That's not good, right? I mean, if you're not doing the experiment, then you've probably made tons of assumptions you didn't realize you were making, and frankly, your work is probably not worth very much. So videos flip this around and say, now, if you build a system, you can video it in action, throw it up on YouTube, get thousands or even millions of people to watch it. And it's really rewarding, because now you feel like you've gotten some recognition for the work you've done. It doesn't solve all of our problems. When you watch robotics videos, you need to be really careful, right? You might be seeing the one time this system ever worked, and it was captured on video, and you think, wow, it's a solved problem. You might be seeing something that is extremely carefully orchestrated. It took 20 takes. The room is instrumented, very carefully measured out. Everything's placed in very specific places. So don't generalize. When you see a video, take it at face value. What you're seeing is what you get. Don't say, oh, now robots can fly through windows. Robots can fly through a window surrounded by Vicon motion capture cameras in a very carefully controlled environment. So these are great steps, but you have to be careful looking at videos. Okay, so these are robot systems that I think we've all seen videos of. I'm a software guy, though. So software in robotics is built the same way that build software in other industries now, where we don't expect people to come in and build from the ground up. Somebody starts and you download a library, a framework. You use a commercial package and you glue it together, right? You take these big units of functionality and you try to figure out how to plumb things. Now, this doesn't always go well because the solution you get off the shelf isn't a perfect fit for your problem. And maybe you could say, I can accept that. It's a sacrifice, but whatever. This software didn't make the trade-offs that I want it to make, latency versus throughput, processing versus memory, or just overall efficiency of resource usage. But with robotics, this is a real problem. Historically, robotics has been very vertically integrated. And the reason being that you have issues like sensors and control loops and software architectures. They all need to be on the same page in terms of timing. Just something as basic as how close to within the expected update rate are we going to run? Because if it gets out of sync, then this robot, like Grisham said, will destroy itself. It's not just going to get a seg fault and you say, oops, or you reboot the computer, worst case. This thing is going to run itself into the wall and keep on pushing until something catches on fire. And this is very expensive and it takes a lot of time. So if the unit of functionality you downloaded and you put together isn't quite right, you say, fine, I can open up the lid of the box, and what I'm going to find inside is surely going to be a box construction kit, right? The box is going to be made of little boxes, but it's not, right? We download some big library, it's not quite right. You look at the source code and you say, oh my God, what is happening? So maybe that wasn't the best strategy, right? I mean, maybe you just leave the box alone. But we can be charitable here, right? We don't need to bash other software. I think one way of viewing it is that when you download some giant web framework or something from some languages that we won't talk about today, maybe they are saying something very precise. It's that big unit of functionality. Maybe if I download a game engine and it says, if you press the go button, you get a game. That's pretty precise. You're getting the game that somebody else invented and all the little details and decisions they made, but it's not the decisions that you would have made. So it's saying something very specific, but it's saying too much. You want it to say, specific things about smaller pieces. And this is what Haskell is really good at, okay? When you download a web framework or a web server in Haskell, you say, oops, this isn't quite what I want. So you take the lid off the box, and you do find a box construction framework. You find subsystems, and you take the lids off of those, and lids off of those. And eventually you find yourself down some abstract algebra or category theory that you wouldn't have thought was even useful, but it's the substrate that's underlying all this. So I like to think of Haskell and Hackage in particular as a collection of tools, really powerful tools. You have Ed Kmet's half of Hackage, and then you have the rest of us. We're all contributing to these pieces that everyone can then use. And the great thing about this is now you can tailor your solution to your problem, right? So everything's just as you want it. The main enabler of this in Haskell is, of course, its type system. It's not the last word in type systems. We'll hear about Agda later. It's not the last word in formal verification. But type systems, even by themselves, are a hard sell. When you try to convince practicing engineers to use types or any other verification, and you show them a bug, they say, well, that's stupid. I wouldn't do that. Because when you look at a bug, most bugs, they are stupid, right? In isolation, it's just a dumb thing. The manifestation of the bug when the system's not performing correctly, that's really fascinating, and backing out what went wrong is extremely difficult. But when you look at the bug itself, it's unconvincing. So what researchers do when they want to push verification is they focus on a few application areas where they say, hey, come on, it matters, right? They don't have to say a whole lot, because you can say, like, are you sure there's no bugs? Because you will die if there's a bug. And then the programmer says, okay, let's run another test. So I want to take a quick look at what Haskell can provide in terms of formal verification for software. So something about these things to note is that, first off, are all of these things robots? I don't know. When you have health monitoring things, these might be classified as cyber-physical systems, where they have some perception and they can make some decisions or something like that, but maybe they don't move. The Mars rovers have limited autonomy, but again, there's lots of software running. The Da Vinci surgical robot, I mean, it's teleoperation. You have these really awesome joysticks. But the verification that we're interested in here is kind of low level and unexciting. Like that bug I showed on the previous page. It's not so great on its own to look at, but in these contexts it matters. So we're going to start simple too. So I built a little circuit for this talk. The pieces are in my bag, and if I have time later, then we can put it together. But the idea is to make a little widget that is a proximity detector. So we have an Arduino, it's an 8-bit microcontroller, we have an IR rangefinder, and we have a button. And so my thinking was this. My thinking was, okay, I have this little widget that when something gets too close, it's going to rapid fire messages over a serial port to the computer. Otherwise, it's going to send messages at a lower rate. So I'm going to say once every second it'll send a message. Unless something gets close, then it sends it 10 times a second. Unless you're pressing the button. And if you press the button, then it'll send it at 10 times a second. So the spec's getting a little wild, right? But this is what happens. Because somebody says, I have an idea for a product, and somebody else says, you should add a button. And then you say, what should that button do? And you end up with a spec like this. But we can manage this, okay? This spec seems a little ambiguous. So this is what's going to be really useful. We're going to use the SBV library. SBV is a package that's available. It's written by Levent Urquhart at Galois. It's a SMT-based verification. SMT is satisfiability modulo theory. These are ways of automated theorem proving by searching through parameter spaces and saying, I couldn't find any reason why your proposition would be false. Therefore, it must be true, because my search was exhaustive. So we're going to use this to write our function. I'm first going to define a couple constants at the top, and then I'm going to define this function f that takes 3 parameters. It takes the current range measurement. A confusing thing is that this range sensor gives higher numbers the closer something gets. Okay, so bear that in mind. We're going to take range, the manual override, and the time since we think we should have last sent a message. So this function is going to output the time since we should have sent an output. If it returns 0, then whoever called it should say, ooh, I should be sending something right now. Otherwise, it's going to be an increasing number. So the idea was to say that, okay, if the range is greater than 200, meaning something's close, then we return 0. If the manual override's triggered, we were going to return 0. If the time since we last sent something is greater than 1 less our maximum time between messages, then we'll return 0. Otherwise, we're going to increment this time step. So the nice thing about having this automated theorem prover is now we can start writing propositions to make sure this is all straight in our head. This is very confusing. So I write the first proof, proposition. It's a function. It says for range, manual override, time. the result of my function f is always less than max time since, which was that ceiling on the interval between messages that we never wanted to break through. The second proof is an implication, that bulky arrow with two equal signs. It says if the range is greater than the safety distance, and remember range goes up as things get closer, so if things too close, then we're going to return 0. And similarly, if the manual override is triggered, no matter what the other parameters are, we're going to return 0. And then I just lumped all those definitions into this spec thing to make it easier to run them all at once. So I ran the proof, and we have a problem. The great thing about SBV is that when it says your proposition's not quite right, it gives you an example of why it's not quite right. So we can look at this set of arguments and say, well, range 0, let's not worry about that. Manual, false, t equals 9. Is that interesting? So range is not greater than 200. Manual is false. So t is 9. Is t greater than 10 minus 1? No. So we're going to return 9 plus 1, 10. Wait, 10 is not less than our ceiling. So that ambiguous wording of, do we allow 10 cycles between messages or do we allow fewer than 10 cycles between messages is now kind of elucidated here. And if I want to say that every 10th cycle through our loop is going to be an output, then I have an off by 1 error. And when we ask SBV to verify this for us, it says, yeah, now you're good to go. Now these propositions that you are restating your spec are fine. So what we don't want to do is throw all the work that we just did out of the window and now hand translate our Haskell function into some other language, namely C. So SBV can generate C for us. And we say, please generate me a C function called output guard here. It's going to take 3 parameters, the R, M, and T. And the return value is going to be that of the function that we just verified. And the C is a little bit ugly. It's machine generated. But if you look at it long enough, you can see that it's doing some weird assignments, but it's fine. And the compiler can see through those assignments and optimize this away. So it's just straight line logic, one operation per line. And actually, I think it's kind of clean. I mean, we wrote this if-then-else thing in SBV. It looked a little funny. When you think about compiling Haskell, you get worried that it's going to have funks or something like this. But no, everything's pretty good to go. And this is a little hard to read, perhaps, but this is the entire source file, right? So why don't people want to use formal verification tools? Because there's an overhead to using them. And they say, I'm going to have to write everything twice. I'm going to need dozens and dozens of lines. This is something like 12 lines of code, right? There's mostly comments and white space in this file. And we've generated a C function that we proved various propositions about. So that's our output guard function. On an Arduino, you have a sort of application structure. You have a setup function that initializes I/O pins. You have a loop function that the library is going to call over and over and over again. So for that, we're going to use another Galois library by Lee Pike called Copilot. Copilot makes a neat kind of abstraction of the Arduino. It says, rather than just, say, reading a digital pin, which is always going to give you a 0 or a 1, treat that pin as a stream of 0s and 1s. It's pretty straightforward, right? It's just invoking that read function over and over again. These are the values you get. So when we want to use Copilot, everything's going to be lifted from single instantaneous values to streams. So much like most Arduino code, I'm going to define some values for specific pins. And then the analog read, digital read are very much similar to the Arduino standard library. And output guard is calling our function, except it's now lifted onto streams of inputs. And it's now returning us a stream of outputs. This gets a little bit confusing, the main spec for Copilot, because we have these streams that we're going to be advancing simultaneously. So we want our logic at the current time step to depend upon previous values, not current ones, so we can maintain some semblance of causality here. And it turns out that this arrangement here, you can see go is sort of delayed by one step with just an initial false, and then it's appended with an infinite stream of comparisons to this prev stream. Prev, meanwhile, is calling our output guards, is using our output guard stream. And we have these 2 triggers, which is what's going to do stuff on the Arduino. We have the one that says print something out if our output guard said we should, and what we're going to print is the range. And the digital write is controlling an LED, because the fun of running code on the Arduino is that you don't have to be connected to a computer. You can disconnect it. So I wanted the LED to flash to indicate that something was going on. And right down at the bottom, you see the little bit of code to now use Copilot's code generation facilities, which in this case is actually using SBV as well. And it generates a lot more. It generates several C files itself. And these are some Arduino specifics. This is also a slide that I don't like. And I hope somebody here, other than me, or maybe me, can write a better library, right? Copilot's fine, there's not really a lot of support for Arduino specifically, but like, look at this. This is pretty straightforward. Why, there should be a package that I can download from Hackage that can maybe do something even fancier. Why don't I have types guaranteeing that the way I initialize the board is compatible with the way I use it in my loop function with respect to I/O directions, which pins are inputs, which ones are outputs. I think we can do that, right? We can lift that verification into the types. So I'd like to see it. Now we're pulling serial data into a computer that's connected. Let's do something with let's not print it to screen, right? Let's be a little bit more ambitious. So this is the kind of logging framework that I use in my own work too, where when you can't decide what to do with the data, you just do everything with it. So we're going to print something that's a standard out, but we don't want like tons of numbers scrolling fast. So maybe we're going to pick out ones that look like maybe the user might want to see them. We're going to dump everything to a comma-separated value file so we can do offline analysis. And we're also going to feed it into EKG, which is something I like for doing online telemetry. EKG sits on top of a Snap server, and it's usually used for monitoring the runtime system of GHC. So you can look at garbage collector statistics and the like. But it also offers you a facility to create your own counters so you can monitor your values while monitoring sort of memory usage, what your allocation rate is, productivity across cores, which is really useful when you have some long-running Haskell thing. But we're going to do this a compact way. We're not going to do this the easy way. Well, I think it is actually easy. So let's pull in a coroutines library, because that's what everyone does, right? Machines is a lot like enumerator, iterates, pipes, conduits, I/O streams, but I think it's pretty straightforward. The core of it is this step data type. It says that, okay, we're going to have a bunch of these little, like these logging things that maybe maintain some internal state if we want to maintain a buffer or something like that. And so each of these guys, they can await data from upstream, they can yield data downstream, or they could say they're done. It's pretty simple. The machine T new type just says, you can do all that to take steps in an ambient monad. If it's I/O, that means you can do I/O when you take a step. So we're going to wrap up serial ports in machines. And right down at the bottom, you see the kind of main export here, which is just saying, take a serial port, I'm going to run the serial machine, push bytes downstream into ASCII lines. Because the Arduino has its own ideas about how to print values onto the serial port, and it uses carriage returns and new lines and things. And, but I think it actually makes a sort of interesting use case, because serial machine is defined rather simply, as you can see, is just repeatedly get up to 8 bytes and then push them downstream. It's pretty brain dead. Whereas ASCII lines is actually defined recursively, and it's not that different than what you might just naively write if you were just writing some function that had some I/O effects or something like that. It awaits bytes. It says, are there any null ones here? Because sometimes that happens when we plug them into the computer. Gets rid of those. It takes whatever it got, adds it into its internal state, and then looks for any completed lines, and then it pushes those downstream. I've also defined a read machine here, which just does the obvious thing of it takes strings and it tries to read values out. Okay, so this was our architecture, which looks a little bit complicated, but we can do all of that diagram in this one slide. The top function is a little bit of fan-out code that multiplexes the data from the one source into the several downstream consumers. But let's look a little closer, because I think this is neat how small these are. The standard out one says, let's just print out values that are greater than 100. If the device is sitting there's nothing in front of it, don't bother the user with it. But if something might be approaching, okay, start printing out values. The CSV one says, I'm going to wait for 50 ranges, and then I'm going to write them all to a file. So I don't want to be opening and closing this file every number we get. The EKG one is launching a web server, and then every time it gets a value, it's going to update it. So you can see the CSV and EKG are doing a little bit of initialization. The CSV is writing a column header to the file. EKG is starting the server. And now logger is this big compositional thing, and it's just a list of these little machines. We can remove one, we can add them, we can drive that via a configuration file, which is the way that I usually use this. And it's really easy. They don't have to know about each other. So what did we do? We wrote a function using SBV. We wrote 3 propositions about it, and we proved them sound. We used Copilot to write an application for the Arduino that had these infinite streams of data coming from I/O pins, and we generated C from that. We wrote a machines wrapper over a serial port. We sent it to 3 different loggers such that we can swap in and out loggers, and it was 151 lines of code. And this is the output that we can generate. I'd love to run this for you right now, but a funny thing about it is that this laptop will sometimes kernel panic. So where are the formal tools? They're not being used. I don't know. That's FTDI's fault for the serial port driver. But after the end of the talk, if there's time, we can try running it. So these are the three forms of output that we're getting from not a lot of investment. All right, microcontrollers are awesome. Buy an Arduino if you don't have one, play with it. If you get bored, it's $20, you're fine. And if you do play with it, try to use Haskell. You know, it's a real case of we need more hands on this code right now. I hadn't actually used it before, but I thought, this is a great opportunity to do so. And it shows signs of neglect. Like, it's got this awesome core, and I think Galois was really successful in their use of it. But for a broader audience, there are some real low-hanging fruit. And I think we can make Haskell a kind of primary language for doing embedded development here, because we're not writing a lot more code than you would write in C. If somebody was writing an Arduino program in C, they're going to write like 50 lines of code. We wrote an extra 100 lines, and look what we did. Like, we're moving heaven and earth here with nothing. So let's take advantage of that, and maybe we can get more of the Arduino community actually to think about using Haskell. Anyways, so we have microcontrollers. Now we're going to do micro robots. Give you a taste of something slightly different. This is a project where this manipulator is at a sufficient scale to deliver drugs to an individual cell. I think that's kind of crazy, right? So deliver drugs to a single cell. Now, they're large cells, granted, but nonetheless. The problem is this is far from being available in your doctor's office, because this all happens on a slide on a microscope. So whichever of your cells needed medicine, you're going to have to remove them and put them on the microscope. I was brought in just to do tracking, because at this scale, a funny thing is that you have lots of issues. The manipulator sticks to the slide surface, even though it's in fluid. So the novelty of this paper, which I'm not a primary author on it, was that you use magnets to drag this manipulator around the slide, but since it gets stuck, you add another axis that just bounces the thing up and down. So it's bouncing at some pretty high rate and being dragged around. So it's moving in sort of funny ways, and at this scale, there's little particles in your fluid that are really hard to not have, and they stick to it. So its shape changes during the run of an experiment and between experiments. And molding things at this size, the fabrication story, I mean, I invite you to look at the paper if you're interested. It's very detailed and it's hard, and they just don't come out the same every time. So we used a lot of different image processing steps here. We're doing all the usual old school things using OpenCV. We're saying dilation, erosion, finding edges, connected components. And I just threw the whole kitchen sink at it and then stuck a particle filter on the various tracked entities, and it worked out okay. So what we're seeing here is what does a computer vision program look like? And I think this is sort of this maybe illustrates some of the difficulty of using OpenCV. OpenCV is this computer vision library. It's got a lot of functionality, but it's kind of built around an imperative mindset. And you run into trouble of when are you manipulating an image in place, or when you're going to copy it. So with this kind of architecture, don't clobber the source image, please, because we have these other pipelines that are going to use it. So you need to grab it, and you need to manage temporary images, image data structures, and it's up to you. And what invariably happens is you end up having to debug this because somebody accidentally overwrote an image you were counting on still being there, and it really messed you up. But there's an opportunity in an architecture like this, which is within these pipelines, there's ephemeral image data going straight down the pipeline. Okay? So when I started on this project, I took Noam Lewis's OpenCV bindings, and I said, well, I was relatively new to Haskell at this time. I should make a pure functional interface. So the way we're going to make a pure functional interface is I'm just going to copy the input before I use it. And that way, if you were holding onto a reference to the original image, you'd be fine. But then I start paying this big overhead because I have these long pipelines, and it keeps on copying images that no one's ever seeing these copies of. So we're doing a lot of memory allocations that are pointless, and we want to not do that. So we're going to do dangerous Haskell programming. All right. We're going to have some FFI library that, here I have some data structure. It's just stuck in an IO ref. I marked it as no inline because the documentation for unsafe perform IO says mark it no inline, just so the side effect's not performed twice. What you're losing when you do unsafe perform IO is the ordering of the effects. In this case, we're actually not doing anything terribly dangerous, so everything's okay. So here's our operation. We're going to update this value in place by incrementing the number that we stored in the IO ref. So the way we make it functional is we say, like I mentioned, we take an input, we're going to duplicate it, and then we're going to mutate the duplicate, and we're going to give you the duplicate. So the original's fine. And I put in a delay here to indicate that there is a delay in reality, too. It's usually not a second, but You know, when you're trying to convince people that your use of Haskell is fine in a setting where people don't use Haskell, and then you're paying a penalty of 30%, say, in performance because you're doing all these copies that are redundant, people aren't sympathetic generally. I mean, they're glad that you're happy with your toy, but still. Okay, so the key part here is that this op wrapper that does the duplication is marked no inline. That no inline is important. So what that means is that whenever you use op in your source code, it is going to stay as that symbol op as the optimizer is running and doing its thing. Whereas inc, which is our increment function, which is pure now, it says give me a my data, I'll give you a new one, is marked as inline. And that means the compiler, wherever it says inc, it's going to try to substitute the right-hand side of the equation into your code. And that right-hand side of the equation has this op wrapper on it. So we'll look at the cost that we're paying for persistence, and we can see, so I said I start with a number 3, I increment it twice. And I duplicated the original input 3, then I duplicated 4, which is annoying because nobody ever saw that, right? So like once I incremented 3 to this value of 4, does it matter if I clobber it? I mean, no one can see it. It's in the period between those two inks, the composition operator. So what we're going to do is we're going to add a rewrite rule. This is an amazing thing that GHC offers. It's very fragile, and it's hard to make things go right. But when you can make it go right, it's amazing, right? Because you're extending the compiler with knowledge that you really desperately need to make use of, right? That the compiler can't possibly know about. So all we're doing here is we're saying if you compose 2 of these op-wrapped things, then just collapse those 2 op wrappers into 1. And what this means is that as something enters a pipeline, it gets duplicated. Once it's in the pipeline, it just gets smashed over and over and over again and comes out the other side. So the consumer sees a freshly allocated value, but you've not been doing these allocations internal to the pipeline. And sure enough, this works, and it scales up quite highly. The more you're composing things, the more benefit you're going to get. Okay, so that's one way we can now have a purely functional interface, which means we can do parallelism and things like that, but not pay a huge penalty for it. So using these traditional 2D vision techniques, we've done a lot of projects. So now we're going to move on to bigger robots, okay? So my friend Ben, who's here, he came to me one day and said, we want you to do perception on a project because we want to do something useful with the robot. Because it's very frustrating seeing all this research done and it's all kind of these like toy demonstrations. And we're like, can't we do something real? I mean, just for once. And this actually was really hard because we said, these are going to be realistic looking objects and the environment, they're not real, just in case you were wondering. On this grass background, and they're quite small. There's a laser rangefinder on this robot that can't really see them all that clearly. But the camera in the robot's head, it's a really nice camera that runs at 2 frames per second, unfortunately. But from this overhead vantage point, we can see pretty much the full circumference of these objects we want to pick up when you project them onto the ground. So now we can localize them with respect to the robot very well. And the scooper mechanically frees us from having to worry about the orientation or anything. You can see there's a lot of symmetry there anyways. So the robot's actually pretty smart. There's no audio right now, but it knows that it missed because it's sensing when something actually fell into its bucket. So what it just said was, oops, I'll try again. And it will succeed. So this actually worked really well. You know, so Ben's really a big motivator of mine because he says everything's too slow and nothing's reliable. So he would stay late at night and run this for hours, I think. I mean, and what was the success rate? 98%, around there? Which is pretty phenomenal for research robotics, right? 98% success rate is kind of unheard of, because usually we just want to demonstrate that something's possible once. And this was sort of another level. And it was great, because we were doing this for a live demo. And you know, live demos, if it worked in the lab 1 time out of 10, it's not going to work live. So Ben was very proud, and justifiably so. Okay, so I said we're going to see all these different parts of robotics. We did microcontrollers, we did micro robots, we did bigger robots, we did OpenCV, and we want to start now exploiting more computational power. So we're going to go straight into OpenGL. This is going to be a big leap because I'm going to use Vinyl records. Vinyl is a library that John Sterling released earlier this year that supports heterogeneous lists, which if you're not a Haskeller, sounds like no big deal, and if you are a Haskeller, then this is amazing, right? So here's what's really cool about these kinds of records. You can see I have this vert type for a vertex, where I'm going to store a vertex position, which is a 3D vector, and I'm going to store a texture coordinate, which is a 2D vector. The power of these records is this. 1, I can upcast. okay, to a supertype. If I want to discard some information, if I have a function that wants only records that have a vertex pos field, then that's no problem. I have a cast function that comes from the library that will do that for me, which doesn't sound very Haskell-y, but it's totally safe. The other benefit here is that while this looks kind of like a map or an associative array that you might see in another language, because we can append on other fields in our code and build up new records in a very ad hoc fashion, that list structure exists at compile time. Now the compiler is going to chew through that before you ever run your program. So you're not paying this list traversal. And in fact, I added a benchmark to the Vinyl package to demonstrate that for numeric computation, if I have something like this where I have various finite vectors that are packed together, there's no overhead from Vinyl at all, right? You could, if you're using a regular Haskell record, or if you're just jamming stuff into a storable vector, there's no penalty because the compiler knows exactly the offset to read data back from your vector, because that can all be computed at compile time. So for OpenGL, this is really useful for two reasons. One, we have that sort of ad hoc benefit. The other reason is that those little field names that are sort of making the code a little bit more self-descriptive, we can arrange for them to coincide with code that we write for our shaders. So we're going to use OpenGL's shading language because I don't want to reinvent a new language that loses some of the expressivity there. Because graphics technology is moving so fast. And I'm wary of things that try to simplify the hardware too much, because I don't want to lose any of the benefit. The whole reason I'm writing code for the GPU is to get speed. If I'm paying overhead, then I'm kind of sad. So what we're doing here is we're reflecting over this record type. So this can all happen at compile time. So this is now a constant in the compiled executable. And it says, oh, you wanted to know how OpenGL wants to know how to index an array of vertices so that I can read out the text coord fields. And this says text coord is a 2D vector of type float. The stride between text coords in an array of verts is 20 bytes. You can see we have a 3D vector, a 2D vector, 5 floats, 4 bytes apiece, 20 bytes. The offset into the array is 12. So it's doing all this automatically. All right, now we're going to race ahead. OpenGL is great. It's wonderful, and it makes pretty pictures. OpenCL is very similar, except doesn't have the graphics baggage. So OpenCL is really handy particularly when your output isn't quite as structured as graphics output. Graphics output says, every pixel, we're going to compute a value for it. OpenCL lets you say, based on this data, I want to draw to that pixel over there. And OpenGL doesn't really want to do that. So OpenCL has some flexibility. This is not the easiest way of running it. I have the CLutil library, which I think is on Hackage, but it's on GitHub if it's not. This is a somewhat more complicated way of using it. We can just feed Haskell vectors straight into OpenCL, which is fine on the CPU because we have this. The way the library works is that it can grab the pointer to the Haskell vector and reuse that. But on the GPU, you do not want to be creating memory buffers and releasing them every time you call some computation kernel. So we're going to pre-allocate some memory here. The CLutil library is providing a lot of safety benefits, though. It's providing these buffers, and it also provides support for images, and it adds types to them to say what are the types of the elements of these buffers or images, and the length of the buffers. So if you try to write too many values to a buffer, at runtime it'll say you're doing something bad, stop. So here we're pre-allocating, we're creating a function that adds 2 vectors, and we can run it. This helper also, you see this get kernel business, that's maintaining a cache of compiled OpenCL programs, so we're not going to recompile things needlessly. So it's pretty compact. This is now running vector addition on the GPU, and we can do that at a pretty high rate. Okay, so we've seen OpenCV, we've seen OpenGL, we've seen OpenCL, and I thought we had to put them all together. So I'd never done this before. I mean, a lot of my work, I use OpenCV sometimes, I use OpenCL sometimes, OpenGL sometimes, and then why don't I just write a program that uses everything? And so I just thought of something weird to do. I want to pull images from the camera on my laptop using OpenCV, use that as a texture in OpenGL, where I'm going to render tens of thousands of triangles in a grid. But I also want to take the image and feed it forward into OpenCV and compute edges, because that's something that OpenCV does really well using very old algorithms, the canny edge extractor, which is great for the CPU because it has sort of irregular memory access patterns. So let's take advantage of our hardware. Let's do edge extraction on the CPU and OpenCV, and let's feed those edges as images to OpenCL, and then let's let OpenCL modify OpenGL's vertex buffers. That's why I have a diagram, because it was very confusing. All right, so this has to be possible. It involves a lot of imports. If you were using this for your own project, you'd probably put these somewhere else, and so you're not cluttering up all your files. The cool thing is that this is it. We're going to do it, right? And this is the list of imports. We're using a lot of libraries, of course. We're using some pieces that I wrote for the vinyl GL package examples, just for using opening up the window and such. But all right, we get those out of here. The language pragmas are really to support vinyl. So Haskell's great at defining geometry. Our little grid definition is not a lot of code, and it defines whatever number of vertices you want, just as you would define them, row by row. Indices now indexes into them, so we don't have to. We're going to render triangles, and you can see in the diagram I wrote on the top right, we're going to have 4 vertices, going to make 2 triangles, so we're going to index into our vertex buffer using this kind of wraparound way, right? So we go a vertex, go down, and go up and to the right, and then we take the second triangle, we go to the right, we go down, It takes a little bit of fiddling to get that right, but again, Haskell's pretty good at expressing that. The next bit gets a little heavy, admittedly. So let's zoom in on it a little bit, because it should look familiar at least. We're going to use images in OpenCL now. This is kind of a funny thing. OpenCL general computation, but hey, it's running on a graphics card. And you know what graphics cards are really good at? Dealing with textures. So you, as a programmer, say, I can look up a value in an array. And a graphics card says, you want 1 value, I'll give you like 8, whatever you want. And I will interpolate them for you, and it's free. So they have that hardware, so OpenCL says, okay, we can use images too. And now you can linearly interpolate your array indices to interpolate then the values that are stored in the array. So we're going to use images. So this is kind of crazy looking now. We're going to, at the bottom here, we're going to return some function that takes a vector of edge pixels, which is an image where all the edges are highlighted, but it's now going to be in a Haskell vector. We're going to write that into an OpenCL image. Then we're going to call this blur kernel. I call it blur. The final effect is not very blurry, because I like what I have here better. But we have these 2 images, so we can ping pong between them. If you want to iterate something like a Gaussian blur, then you're going to want to read from one, write to the other, read from that one, write to that one. And then we call our OpenCL kernel with that run kernel CL. We pass it the edge image. We pass it the vertex buffer that OpenGL is going to be working with. And we have just a 1D work. So we're going to have a work item for every vertex in this case. OpenCV part. We haven't seen much OpenCV code, but there's a composition operator there, which now we're all aware might hide something pretty frightening. But create camera capture gives us an I/O action that's just going to give us a new color image. And so once we've got that image from VidCam, we are going to convert it to grayscale, run it through the edge detector, push the edge image to OpenCL, and we're going to also take the color image and upload that to OpenGL. After all that importing, it was 109 lines of code. That's including the imports, actually. All right? So again, lines of code is a terrible metric, and by no means is it something that you should really depend upon at all times. But I think that's pretty good, right? I hadn't combined these libraries ever before, and it's a pretty small application. And I think I'm doing okay on time, so let's just see. I'm going to see if that can run right now. Let's see. What I really like about this is that you're doing a lot of processing, right? We're doing 20,000 triangles, we're doing the image processing, and at the end of the day, when this is running on my laptop, which is not a particularly new laptop, it uses 20–30% of the CPU and 10 megs of RAM. Like, it's nothing. And if you're not using the GPU and you try to, I have the window open on my screen, you can't see it. If you try to do this on the CPU, then you experience pain. So let's, this is all now a 3D display. Let me get a look at my arm. So I don't know why you would want to do this in particular, but it seemed worthwhile to me at the time. I think it is a good demonstration, though, right? So you're saying that we can harness all these libraries in a pretty small amount of code. So nothing to be afraid of. You're not looking at a mountain of work to get things up and running. All right, let's go back to the main show. Okay, so we looked at a robot picking up poop, which may have been a new experience for some of you. We were very proud of that. It could pick up more than one per minute, which was our goal, but it's still kind of slow. And when you see videos using that robot, which is the PR2 from Willow Garage, they are often sped up 10 times or 20 times or even 100 times because the robot's not that fast. But then the problem is, I think researchers think that lets them off the hook. If the robot's slow, why does my software have to be fast? That doesn't seem right. But that's nonsense, right? Robot videos should be better than what they are. So we decided, okay, speed is now going to be a core feature of what we're going to do. We're not going to let the world sit still and the robot takes its sweet time to decide what to do and then do it. Now the world is going to come to the robot at whatever speed the world runs at, and the robot has to deal with it. So we're going to have moving objects, and the simplest way to do that is have a conveyor belt. So we bought a conveyor belt, we went to the dollar store, and we bought things that looked interesting, all to accompany the $120 sensor mounted above the robot's head, which is all we're going to use for this. So this is a bizarro picture, I think, okay? This robot costs $300,000-$400,000, and we're going to focus on the $120 sensor and these dollar items. They're the key players here. Okay. Before I proceed, I will point out, because I tend to forget to remind audiences of this, that all the perception work you're going to see here is done in Haskell, in case you were doubting. All right, so let's break this problem down. This is what the robot's looking at. An interesting aspect of this view to bear in mind is that when something's coming towards you, you're seeing the near side of it only. You're not getting a good view. Remember, we were picking up poops, we could look down and see the whole perimeter. So if we picked like the center of mass, then it was pretty accurate, actually. Here, we're going to see the side of the object nearest us. So our estimate of its centroid is going to be biased towards us. We're using the connect, which gives us 3D data. So this is the depth image that it sees, where the brightness of the pixel is proportional to the distance. If you've been doing computer vision for a long time like I have, this kind of image is amazing, because if all you have is color, and if I hold my hands up like this, it's hard to tell if there's a space between them or if there's one thing, because the colors are similar. And you always have overlapping objects. You think it's an uncommon thing until you program a robot to navigate the world, and then all of your worst nightmares come true, right? This is why the robot inevitably ends up in a corner staring at the wall, thinking, there's nothing here, why can't I move? That will happen. So now we have this depth sensor, so we see that, and in no time flat, we've broken the scene down into parts. I mean, this is a huge step from just an unstructured big mess of colored pixels, right? Now we're saying, oh wait, there was floor down there, this giant planar thing. Forget it, I don't care about the floor. I have my arm in front of me, I have the chair, and most importantly, you can see the table. We did this in 2D. We just did 2D processing on the 3D data, so it's very fast. That takes a few tens of milliseconds. Now what we're going to do is we're going to track the table, because we're doing a mobile manipulator. We can't compete with factory automation and just raw speed of an arm moving, but we can have a robot that can drive into the room, turn on the lights, and drive up to the belt, turn on the belt, and then start working at it. That's pretty cool. So we're going to keep track of the table so that if the robot moves, if we have to reposition it, or if somebody bumps into the table, we don't have to abort the experiment. The robot's going to keep track of where everything is. We now need to teach the robot about our objects. So we scan them in using the connect. This was a very ad hoc process because we were lazy. But what I like to say is that this really tested our system, because the data we gave it was very noisy. And if we could deal with this data, imagine what we could do with good data. So we capture these models, and now our challenge is to say, given a partial observation of this model, exactly where is it on the conveyor belt in front of us? So this is a 2D pose estimation problem, where we have translation and rotation about a vertical axis. We're going to do 3D recognition so we can know what the object type is. So we want to recognize the object. We're going to say, aha, that is an imitation croc. I can see part of it. Now I'm going to take the model I had for the croc and figure out how my observation works on that. And we do that through a nonlinear optimization. It's actually through a really simple method. It's Powell's dogleg nonlinear optimization. And that code's open source, and that is on Hackage. And we're going to do all that on the GPU. And the reason we're going to do it on the GPU is because the way this nonlinear optimization works, a lot of optimization problems have these beautiful closed-form solutions, and when you get to really hard problems, the solutions are amazingly ugly. You're basically just saying, here's a parameter, does that look good? No. Here's another parameter, does that look good? And we just do that a lot. And we do hundreds and hundreds and hundreds of attempts at translating, and we slowly converge on something that looks really good. And the way the GPU is really good at it is now we have 3D data for this model. put a cube around it, and at every voxel of that volume, put the distance to the model, okay? Now when I take 3D points as input that the Kinect is observing, I can texture them with that cost function, and then I'm going to integrate over all those points, which again, the GPU is pretty good at. And I'm going to get a number, and that's going to be the total cost of this pose for this observation with this model. So we're actually going to pick out a couple models and try out which ones work best for any given observation. And once we do all that, we can establish coordinate frames. So we have a coordinate frame for the object. We have a coordinate frame for the robot's hand. We can then teach the robot how to pick things up by moving its hand. We say, robot, here's the object. Now put your hand here. And we're going to record that relative to the object. And that's going to be, in our case, what we call a pre-grasp pose. And then a second pose that's going to be in contact with the object. So this is going to be like an open loop motion. It's going to be colliding with the object. It's going to be kind of ugly physics things happening. But we record these in the coordinate frame of the object. So now when this object's been translated and rotated and is coming towards us at hopefully high speeds, we're going to be able to say, okay, take that hand pose, transform it into the object's coordinate frame, and now we've compensated for how this object differs from what we recorded when we were doing the training. And so, we set out at this, and the state of the art for a mobile manipulator was running at like 6 centimeters per second it could handle for objects on conveyor belts, which is really slow. And when you look at a video, you say, wait, it's not moving. Oh, wait, no, okay, it is moving. It takes a couple times. And we wanted to get to 10 centimeters per second. That was our, we will declare victory and go home. And it came together pretty well. So we started out here, just a static test. This object's terrible to pick up. The gripper's so big compared to those triggers around that spritzer bottle. These baskets, the handle's this wide, the robot gripper is this wide. We have about 1 centimeter to spare on either side. So this video is one take, too, I will point out. This is from inside the basket. It was a little rough on the camera, unfortunately. Admittedly, that was one take. It was a good take. I mean, we were happy with it. It wasn't just like, I'll take the first one we get. But so yeah, we're running at over 1 foot per second. We're doing 3D object recognition and 2D pose estimation at 20 hertz at the end of the day. Pretty consistently, too. So a lot more is involved in that project. You can talk to Ben if you're interested in planning in high-dimensional spaces or mobile manipulators in general. I'm just the perception guy. So now you know what experimental robotics looks like. There are big robots, and there's most of your time spent at a keyboard. But Haskell's a great tool for it all. Thank you. Do we have any time for questions? Are there any questions?
We've got a mic. If you raise your hand, I'll bring the mic and ask the question.
Somebody tell me what a robot is. Is anyone? Yeah.
I'm not totally clear on what the architecture you are running on is. Did you ever have any issues with garbage collection or any of the issues that people generally have running a language like Haskell on a small or embedded system?
So that robot is not a small or embedded system. It's got a lot of computers in it. But garbage collection is still a problem. I mean, I say 20 hertz. I didn't talk about another aspect of this. I talked about model recognition and pose estimation. We're also tracking it over time because we want to see how it's moving, because we don't know how fast the robot doesn't know how fast the belt's going. We could track the speed of that object to within a fraction of a millimeter. We tried to estimate how correct we were, and we couldn't measure it any more closely than what our system was giving us. So what this comes down to is we actually require several successive observations, and we run a Kalman filter on the pose of everything, okay? Now, you throw a delay into this at the wrong time, and it can cause problems. But what we do is we manually trigger the garbage collector when there's nothing coming towards us. It's not brilliant, and yet the EKG monitoring, super helpful at that point, right? Because even though EKG is only updating at 1 hertz, there were actually times when the robot would violently miss an object, and I could look at a plot, and it would say, oops, the GC just spiked on me, you know? So it was actually a really pleasant fix, because I was worried, is this going to be a deal breaker? People say you can't use Haskell because of the garbage collector. I have had papers rejected because people don't trust that garbage collectors could possibly work. And the only way that we can combat that is by just doing the experiments and say, try to compete with us. If you can't, then maybe you're not right, So garbage collection can be an issue, but I think you can manage it. Now, I showed the Arduino code. If garbage collection truly is not an option for you, then yeah, you could still use Haskell, and you can still get all these great benefits and generate code. So I think it's a tractable problem to deal with those garbage collection pauses. Anyone else? All right. Well, thank you. Oh, yes.
So you said that your thing was grabbing stuff at for a foot per second.
Yes.
Did you try throwing it at it?
No. So the question was, I proudly claimed objects are coming at us at a foot per second. Did we try throwing something at it? We did not. There's a wonderful video from another group of a robot catching balls. Now, the way that they did that is through all 2D processing. They threw tennis balls at it, and it could extract a circle, and then see how the circle's scaling, and then fit the trajectory, and then catch the balls. It's pretty impressive. We're not solving that problem, and we're making this huge simplification that we're doing 2D pose estimation. So all of our objects are sitting on the table. The other problem is that, the thing that we battled with the most probably is that the PR2's hands are not made for doing this kind of thing. They're not soft, they're not compliant at all, and they have big, thick, chunky fingers. So when the candlestick hits the fingertip, it just, falls off completely. Catching a ball, you really want to compensate for the trajectory of the ball. If you can wrap up on it, so the robot that I mentioned, I think it has 3 fingers, and they can kind of wrap over the ball as the ball is impacting the hand. The kinds of manipulation that you can do depends a lot on your hardware. But yeah, I'd love to throw stuff at the robot. In fact, Ben had to stop me from doing that. He would always put, padding on the robot, because when objects are falling down, he says, oh my God, this is a big expensive robot. I think it's hilarious though. I mean, like these objects. Yeah, go ahead.
How long does the robot need to see the object to be able to figure out where to catch it?
Arbitrarily, I say I want to see it 3 times. And we're doing that in 50 milliseconds, so that's 150 milliseconds, until we say, I'm confident of what I've seen and where it's going to be. Because the planner has to now anticipate and say, when is it going to be someplace I could grab it, right? So I say 150 milliseconds. It's really kind of arbitrary, and it's something that you can dial up and down. If you have a lot of noise, we did deal with the fact that other people in the lab would sometimes put random items on the conveyor belt and wanted to not be confused by them. And that wasn't so hard to do, because we do this object recognition stage. So that choice of 3 was really one of those things that, like I mentioned, customize your software for your robot and your environment and whatnot. But that would have to be a dial that you would expose to an eventual user of the software.
So if it was longer, if the conveyor belt was longer, you could go faster?
We would handle faster moving objects, perhaps. I think we would hit real problems with the hands of the robot, because they're just so stiff. The Kinect's depth resolution falls off over distance as well, so it is getting worse and worse. This may have been a sweet spot. We didn't know. We bought a conveyor belt. We don't know anything about conveyor belts. But Ben's really good at finding stuff online. And he showed up one day with a conveyor belt. And it turned out to be that length. That's a standard length. And so we worked with that. That's why I like doing experiments, right? Because these questions, how long should a conveyor belt be? That's not the right question, maybe. Maybe the right question is, how long are conveyor belts? Apparently, conveyor belts are yay long. And, they come in segments like that. And so we just adapted to that. Yeah?
Could it deal with rotation?
Yeah, absolutely. I mean, you could see it adapting to those baskets coming down. The question was, can the robot deal with rotation of the objects? So the grasp that we pick, what would happen is if sometimes the basket or a shoe was coming down, Ben's planner would try to plot a grasp using one hand, and if it couldn't, it would try the other hand. And so it really needs to know the orientation.
What if it could be rotating on its way down?
That would be mean. I don't know why you would suggest that. That's just perverse. Yes.
Did you mention you were going to talk about Agda?
No, somebody else is going to talk about Agda, though. You're looking forward to it.
You mentioned Agda a little while ago.
Yeah, I said somebody else is going to talk about it.
So do we want to move on to the active talk now? Have for any more questions? Maybe one more? Cool.
All right.